whatever time it is where you are in the world. If you're ready to start, Lau, we shall begin. It's my great pleasure to introduce Lau van der Dries this morning, who is going to give the first of two talks in this workshop as a prelude of more to come, which I think Lau will tell us about in a moment. So Lau, take it away.
Okay, thank you very much. I'm happy to be back at the Fields Institute. And as many other people, I have good memories of it. Although this time it is only virtual, I hope to be really back in a month or so in Toronto. But for now, I'm talking from home. Let's see. Everything I say is based on joint work with Matthias Aschenbrenner and Joris van der Hoeven, with whom I have collaborated for the last 25 years on this project. And in 2017, we published our book, Asymptotic Differential Algebra and Model Theory of Transseries. And the focus there was on understanding the differential field T of Transseries. But in the process, we developed a wide-ranging theory of rather general valued differential fields. And to apply this to Hardy fields, which are also valued differential fields of a certain classical type, we had to refine the machinery from that book considerably. Now, the book is mainly algebra, right? Differential algebra, valuation theory, also some model theory. But Hardy fields are not just algebraic in nature, but they also are analytic objects. And so to attack the problems about Hardy fields, we had to also use analysis of various kinds: real, complex, functional analysis, ODE theory, etc. And this work on Hardy fields has taken place in the last 5 years, and I expect it to be beneficial also in other directions beyond Hardy fields. So in the first of these two workshop talks, I give an overview of results in our book. So I'll discuss the key facts about T, the differential field of Transseries, and its model theory. And Hardy fields will just be mentioned in passing. That's in the first talk today. In the second talk on Thursday, I will introduce Hardy fields in more detail and state the two conjectures that we arrived at in about 5 years ago. And about 1 year ago, we managed to prove the first of these conjectures. And last August, also the second. But it's rather intricate material, and we are still working on a good exposition of it. And this course that I'm going to give will also help in doing that, I think. In the second talk, I will try to outline the ideas behind the proofs of these conjectures about Hardy fields. Okay. In both talks, I will try to mention open problems. And in the second talk, I might also speculate on potential connections to O minimality. So that will relate to other interests of people in this workshop. So you can even think of Hardy fields as a kind of one variable version of O minimality, right? Hardy fields, the elements in a Hardy fields are basically functions in one variable, or more precisely, germs of functions in one variable, real valued functions. And the key thing that makes them a Hardy field is that there is no oscillation. And so this is just like in O minimality. Or you can actually make a more precise connection. You can say if you have an O minimal expansion of the field of real numbers, then the fields of then the germs of definable functions defined on some interval from or actually just the field of definable, if you take the germs of all definable functions from R to R, and the germs taken at plus infinity, then they form a Hardy field. Right. But it would be very interesting to go the other way, to start from a given Hardy field with various nice property and be able to then produce an O-minimal expansion of the field of real numbers. But that's some of the speculation that I want to go into. Okay, so these talks are meant as an introduction to my course with the same title, which will then start next week. And there we will treat everything in more detail with careful definitions and proofs. But I will have to rely sometimes on the literature, like the book. And with some luck, we will be able to solve open problems during this semester on Hardy fields. Okay, please interrupt if you want to ask a question. Okay, what are Transseries? That's the focus of the talk today. Well, they are basically series in a variable x built up using exponentiation and logarithms. And here is the typical example. You have e to the x plus, and then in the exponent you have itself, the exponent itself can be a Transseries, right? E to the power e to the x plus e to the x over 2 plus e to the x over 4, etc. And then you can have infinitely many terms, but after an omega series of such terms, you can still have other terms, like at the end here, e to the minus x and e to the minus x squared. So you should think of x as positive infinite, as bigger than every real number. And the monomials here, we will call transmonomials. And as you see, and they are arranged from left to right in decreasing order. So the biggest term, the leading term here is e to the power e to the x plus, etc. Yeah, this is the leading term. And of course, there can be real coefficients in front, like -3, 5, etc. Right. So the idea is that Transseries are obtained by starting with ordinary Laurent series in the variable 1 over x, and then closing off under exponentiation, taking logarithms and reasonable infinite sums. And the precise construction requires well, a lot of care, actually. Let me highlight in this Transseries, a few important parts. For example, this is the infinite part of the Transseries. These are this consists of the terms that are infinite in size, so to say, right? Then you have a constant term, 1, in this case. And then you have an infinitesimal part, which is this, yeah, 1 over x plus 1 over x squared, etc. These are the infinitesimals. This whole thing is here the infinitesimal part of the Transseries. Right, the transmonomials form a subgroup of the multiplicative group of positive elements. Yeah, T with this symbol bigger than here is my notation, or our notation, for the multiplicative group of positive elements. And if you fix a Transseries, the set of transmonomials that occur in it with a non-zero coefficient is always countable and reverse well ordered, right? You start with a big thing and then something smaller, and then again something smaller, and so on. And for example, the ordinal, the corresponding ordinal to this Transseries that I gave here as an example is omega plus 2, right? You have a first term, a second term, etc. And then after you have omega many terms, but then there are two terms at the end. So that's why you have omega plus 2 here. The plus 2 is due to the two transmonomials here at the end. But in principle, the ordinal can be any countable ordinal. And sums and products of strand series are defined as you would expect. And the fact that products are possible comes from this reverse well-ordered restriction in forming trend series. Okay. Oh, I should, right. So since I talked about trend series being obtained by exponentiation and taking logarithms and infinite series, I have to say how we exponentiate a trend series. So to exponentiate a trend series f, let f infinity c and epsilon be its infinite part, its constant term, and its infinitesimal part, as I indicated for this in the specific example. So f is f infinity plus this constant plus the infinitesimal part. Then what is the exponential of f? Well, it is simply you exponentiate the infinite part, you exponentiate the constant part, the constant term, and you exponentiate the infinitesimal part, and then you take the product. Now, you have to explain what we mean by that. Here, e to the power, the infinite part is actually always a transmonomial, and all transmonomials are obtained in this way. Now, e to the power c is just the real number the notation suggests, right? E to the power c. Where c is a real constant. And the e to the power epsilon is simply obtained by expanding the usual Taylor series for exponentiation at epsilon, right? So this gives you the basic idea of how you construct trend series. So to take now, but it's one cannot just obtain trend series by exponentiation and infinite summation. You also need taking logarithms. So to take the logarithm of a positive element, yeah, I should actually say something about the ordering. If you have a trend series, it has a leading term, right? It's a real constant multiplied by a transmonomial, and the ordering of the field of trend series is such that the element, your trend series is positive if the coefficient for the leading term is positive, right? So if you factor out the leading term, you get a constant times e to the power g, which is then a leading transmonomial, times 1 plus an infinitesimal. C, a positive real number, e to the g, the leading transmonomial, and then the infinitesimal epsilon. And then the log of f is just what you think it should be. It's you take the log of this transmonomial, so that gives you g. You take the log of this real constant, and then you take the log of 1 plus epsilon according to the Taylor series for the logarithm of 1 plus something small. And that gives you then the infinite part of log f, the constant term of log c, of the constant term of log f, and the infinitesimal part of log f. So exponentiation is an isomorphism of the ordered additive group of T onto the multiplicative group of positive elements, and the inverse is given by log, just like with the real numbers, right? In fact, if you take the field of real numbers with exponentiation, it's elementarily equivalent to the field of trend series with the ordered field of trend series with exponentiation. Okay. It means it has the same elementary properties, the same properties that you can express in the language of ordered fields with exponentiation. Okay. Yeah, a little bit more on what kind of restrictions one needs when you formed trend series by infinite summation. So it will be useful to introduce a bit of notation here. I will let En be the nth iterate of x under exp and Ln the nth iterate under log. So for example, E sub 3 is e to the e to the e to the x, right? And L sub 2 is log of log x. And these are, of course, very particular trend series. And in fact, they have a special status within the field of trend series. Namely, they are exactly the positive infinite trend series, all whose iterated logarithms happen to be transmonomials. Right. And now a key restriction in forming infinite sums is that for each trend series, there is a finite bound on the nesting of exp and log that you allow in the transmonomials. So for example, and that's why I introduced these E sub n's and the L sub n's, if you have E sub 0, 1 over E sub 0 plus 1 over E sub 1 plus 1 over E sub 2 plus 1 over E sub 3, etc., this is a perfectly fine series, but it's not a trend series because the exp here is the nesting of exp gets bigger and bigger as you go on, as you take more and more terms in your trend series. So that's not allowed. And likewise, 1 over L0 plus 1 over L0 L1 plus 1 over L0 L1 L2 is also a perfectly fine series. In fact, these series lie in a certain spherical completion of T, but it's not a trend series. It's not in T itself. And this, so there is indeed a natural spherical completion, but it's no longer closed under exponentiation. Right. I want to make another remark about these. About these E sub n's, namely that well, the E sub n's are cofinal in T, so every trend series is below one of the iterated exps. And likewise, if you have the strictly decreasing sequence of iterated logs, they are all still positive infinite, bigger than every real number, but they are co-initial in the set of positive infinite elements of T. So T, oh yeah, this is a typo, T bigger, T, I should have written here bigger R, bigger than R, not T to the power R, T bigger than R, as my notation for the positive elements of T. Yeah, that means every positive element of T is above one of the iterated logs. Okay, any questions so far? Of course, all this will be, you can read in more detail, for example, in Appendix A to our book. I will probably, in my course, assume that people will go through that appendix themselves, but here I'm just giving the basic ideas of how these trend series look like. Okay, we are mostly interested in T as a differential field, or if you like, as an order differential field. Here are some key facts about T. It's a real closed ordered field extension of R, right? The real numbers themselves are trend series. And you can always, to differentiate a trend series, you just do it term by term. And this can lead to interesting cancellations. For example, if you take this trend series, the sum over all n factorial x to the power minus 1 minus n e to the x is a perfectly fine trend series. It's actually a divergent series if you think of it as a series in a real variable x for a large x. But if you differentiate it, you get something very simple, namely e to the x over x. So these things can happen. So this is also one reason why we allow also divergent series. If you want to be able to integrate series like e to the power x over x, well, you have to, then you basically end up with this one. So, yeah, so this is, well, anyway. So this differentiation operator gives you a derivation on this field, and so this makes T a differential field. And one can show that the constant field, yeah, the elements whose derivative is 0, the Transseries whose derivative is 0, are just the real numbers, nothing else. It takes a bit of work though, it's not obvious. And also actually defining the derivation carefully, all these things take some effort. And then one can show that every element can has an integral, has an antiderivative. So there is a Transseries whose derivative is f. Again, this takes a bit of effort to prove, but these are all standard by now. Yeah, the history of Transseries is itself interesting. They really became popular in the 80s for various reasons, and were introduced by a number of people, but I'm not going to go into that now here. Yeah, what is important also about Transseries is that there is a dominance relation, or evaluation, if you want. And it will be useful to have some special notation here, which will be used throughout the course, and which goes back to Hardy and Dubois-Reymond, which is very handy. So F is dominated by G, or weakly dominated by G, perhaps, means that in the ordered field, the absolute value of F is less than or equal to a constant times the absolute value of G, right? So you can also think of it as F is big O of G in the Landau big O notation, or big O little o notation. But for us, this is a more handy notation because it already suggests things like transitivity of this. It's kind of a pre-ordering. Okay, F is asymptotic to G, means that F is weakly dominated or dominated by G, and G is dominated by F. And F is strictly dominated by G, is F is dominated by G, but not asymptotic to G. Yeah, so obvious, here is a typical example. 0, of course, is strictly dominated by everything else. E to the minus x is strictly dominated by x to the minus 10 with etc. 1 is strictly dominated by log x, etc. I think this will all be. Oh.
So may I ask a question?
Yeah.
So what is the absolute value of f for Transseries? It's just the highest term?
No, it is f itself if f is positive, and it's minus f if f is negative, right? T is we are T in an ordered field. So in an ordered field, you just define the absolute value as just like in the real numbers, right? It's the number itself if it is positive, and minus the number as negative.
Thank you.
Right. And the constants here are, of course, the real numbers. Thanks. Yeah. I'm not used to this kind of thing. Anyway, one of the nice things about Transseries and Hardy fields and similar valued differential fields is that you can differentiate and integrate this with these relations, right? If f is dominated by G, even only if f prime is dominated by G prime. But there are a few conditions that you have to check. Namely, I'm only claiming this equivalence for when f and G are non-zero and not asymptotic to 1, right? Because if f is, for example, a constant, then f prime would all, yeah. Anyway, this is, you need to check certain conditions for this equivalence to hold. Equivalence holds, right. So this is extremely useful. Okay. Now I have to. Okay, so we are going to now go a little bit in the direction of model theory. We want to consider T as a valued ordered differential field, right? That means model theoretically, we are going to view it as an L structure, where the language L has the following primitives. You have symbols for 0, the elements 0 and 1, and for the addition, subtraction, and multiplication operations. You have a symbol delta for the derivation. You have a symbol for the ordering, a relation symbol, and also a binary relation symbol for the dominance relation. So, yeah, we talk here about the valued differential fields because the dominance relation is just saying, well, F dominated by G is simply another way of saying that the valuation of F is greater than or equal to the valuation of G. When you talk in the language of valued fields. So yeah, we can make this a bit more general. More generally, it can be any ordered differential field with a constant field C, namely consisting of the F's whose derivative is 0, and this automatically yields a certain dominance relation on capital K by the same equivalence as we used to define it for the Transseries. F is dominated by G if and only if the absolute value of F is less than or equal to a constant times the absolute value of G with positive constant C, right? And we can view K accordingly also as an L structure because all these, it's a differential field, so all these ring operations and the derivation have a natural meaning, and it's an ordered field, so the ordering, so this symbol makes sense, and then it's, and here we just defined how to interpret the dominance symbol. And this also, yeah, so this dominant symbol is simply a way to talk about evaluation. So, but it might be useful to introduce explicitly the valuation ring of this valued field, namely, it consists of all the elements whose are F which are dominated by 1. And which is simply the convex hull of C in capital K. In other words, it consists of all the elements in K whose absolute value is between two constants, between two elements of capital C. And this is this valuation ring has as its maximal ideal the elements that are strictly dominated by 1, and we think of those as infinitesimals, right? So they are the elements that are smaller in absolute value than every non-zero constant, than every element, non-zero element of C. Oh. Okay, so now let me see. Yeah, so one concept that will play a big role in my course, and also I needed to state some of the main theorems about T, is the notion of an H field. Yeah, H, well, it's a kind of generalization, a first order version of Hardy field. And the H is because several pioneers in the subject, like Hardy and Hahn and Hausdorff, they all have an initial that starts with capital H. So it seemed reasonable to give this, to use the term H field here. So an H field is an ordered differential field where for the moment the ordering and the derivation are not related, but if they are related in the following way, then we call it an H field. Namely, if F, all the elements that are bigger than all constants have positive derivative, and if every bounded element, yeah, every element in that is bounded by a constant is equal to a constant plus an infinitesimal. So T is an H field, and more generally any differential subfield of T, any subfield of T closed under the derivation, which also contains all the real numbers, is also an H field. Right, and Hardy fields, which I will talk about more on Thursday, are also H fields, provided they contain the real number. There are also Hardy fields like that do not contain the real numbers, and that are not exactly H fields, but pre-H fields, which I will maybe define, which will certainly define in the course, but maybe not now. Oh. Right. Yeah, so now, of course, H field is a first order notion, right? You can see that here, the constants are definable. The field of constants is definable in the differential field K, and you can express these first order sentences. But T has further basic first order properties that go beyond that, namely its derivation is small, and T is Liouville closed. And what we mean by small is that if all infinitesimals F also have infinitesimal derivative, then we call the derivation small, right? And Liouville closed is if you can solve all first order linear differential equations in it. And it also has to be real closed. So an H field K is said to be Liouville closed if it is real closed. Yeah. So every positive element is a square, and every odd degree polynomial has a 0, just like the real numbers. And for every F in K, there are non-zero elements in capital K, such that G prime is F. Yeah. So you can integrate F, and you can also logarithmically integrate F. In other words, there is an element H, non-zero, whose logarithmic derivative is F. Yeah, H dagger, this symbol dagger here, is our notation for the logarithmic derivative. But this simply means you can solve first order linear differential equations in K. Right, and so these are also important facts about T. And also true about many of the Hardy fields that we will talk about on Thursday. Okay, but now something much stronger. This really goes far beyond the first order properties that I mentioned so far. But it's still of first order nature, namely it can be expressed by an axiom scheme in the language of ordered differential fields. We call it the differential intermediate value property. It says that for every differential polynomial in one variable, y, that means a polynomial in the variables y, y prime, y double prime over k, and any elements f less than g in k, such that pf is less than 0 and pg is bigger than 0, you can always find a y in your H field between f and h. Oh, there's a typo here. The h should be g. Yeah, there's a y between f and g, such that py is 0. Right? Just like the ordinary intermediate value property for polynomials over the real numbers. Right. So this is quite striking, I think, such a property. But it actually is a property that T has. And it actually gives you a full, complete axiomatization of the theory. Right? In other words, all first order properties, all properties that you can express by in the language of ordered differential fields, or ordered value differential fields, are actually consequences of the following axioms satisfied by T. The theory of T is completely axiomatized by saying that it is an H field with small derivation, saying that it is Liouville closed, and the real heavyweight saying that it is has the differential intermediate value property. Yeah, actually, of course, to show that it has the differential intermediate value property is not at all easy, but it's true. But what I should confess now that it's a bit of an afterthought. We didn't mention the IVP in our book at all, and we mention it here mainly for expository reasons, because it's very easy to explain what the IVP is. At least I hope so. Right. So yeah, let me say a bit more about why it is an afterthought and not really in our book. In our book, we proved the theorem above with DIVP replaced by two more technical but far more fundamental conditions on an H field, namely of being Omega3 and Newtonian. And of course, these will be important things explained in the course. And we noticed only afterwards that these two conditions are equivalent to DIVP, at least for Liouville closed H fields. But the conditions themselves are a bit technical, far more than DIVP. So I won't give precise definitions right now, except to say that Omega3 is basically saying something about solutions of homogeneous second-order linear differential equations, and that it is an amazingly robust property. It has really striking preservation properties, and is in particular preserved when you pass to any differentially algebraic H-field extension. So if an H-field is omega-free, then any differentially algebraic H-field extension of it is also omega-free. Yeah, differentially algebraic, I should perhaps explain that if you have a differential field and a bigger differential field, then the bigger differential field is said to be differentially algebraic extension of the small one if every element in the bigger one satisfies a non-trivial algebraic differential equation over this small one. Yeah, it's the zero of a non-zero differential polynomial with coefficients in the small one. Yeah, and Newtonianity is actually an axiom scheme, and you can think of it as a powerful version of differential Hengelianity. Yeah. For ordinary valued fields or local rings, you have the notion of Hengelian, which basically says that polynomials which you can solve modulo the maximal ideal in a non-singular, if you have a non-singular solution of your equation modulo the maximal ideal, then you can lift the solution. And differential Hengelianity is also something like that for differential polynomials. But Newtonianity is a kind of twist on it, which well, I cannot explain now, but it's quite powerful. Right. And to simplify our terminology, I'm going to say that by an H-closed field, we simply mean a Liouville closed H field, yeah, having DIVP, having this differential intermediate value property. So these are, and so the above theorem, which I mentioned from our book, is basically saying that the theory of H-closed fields with small derivation is complete, right? Note that in the notion, the definition of H-closed, I did not include small derivation as part of it. It's better to keep small derivation as a separate condition for various reasons. But the theory of H-closed fields with small derivation is complete. Without small, if you don't include small derivation, then the theory is not complete. in fact, it has two completions. One where you impose that the derivation is small, and the other where you impose that the derivation is not small. Both are complete extensions of the theory of H-closed fields. But T is a model of this one. Right. What we really proved is much more, namely a theorem that throws light on definability and what is definable in T, and also on the intrinsic role of this concept of H-field. Namely the following. The theory of H-closed fields is model complete. Yeah, I don't know if I can assume this concept to be known. Again, in our book, there is an appendix of 50 pages where we fully expose the model theory involved in everything we did in the book, Appendix B. So, and of course, model completeness is there fully explained. But you can basically say that the H-closed fields behave a bit like they have a Nullstellensatz. If you have an H-closed field and you have a system of differential equations, finite system of differential equations, any finite number of unknowns, and you can solve it in an extension, in an H field that extends your H-closed field, then you can already solve it in your H-closed field itself. So it's a kind of a combination of completeness and a Nullstellensatz. Yeah, the other thing is that H fields always embed in H-closed fields. So in more technical jargon, one could say the theory of H-closed fields is the model companion of the theory of H fields, right? So there is an intrinsic connection between the theory of H fields and the theory of H-closed fields. And the theory of H fields has a unique thing associated to it, namely its model companion, and only very few theories have a model companion. But if it has a model companion, there's only one, and it turns out to be, in this case, the theory of H-closed fields. I already mentioned that this theory is not complete. It has models whose derivation is not small. For example, if you take T with the usual derivation with respect to X, replaced by the derivation with respect to T, where T is 1 over X. Yeah. So of course, this derivation is definable in terms of that derivation, namely by this formula, by this identity here. Right. So, and these are the only complete extensions of this theory. One where the models are small, where the derivation is small, and the others where the derivation is not small. Right. Any questions so far? Okay, I have to keep track of time, I suppose. Let me see. Oh, an interesting byproduct of the proof is that and that is actually a justification for the term H-closed. If you have an H-closed field, then you have no proper differentially algebraic H-field extension with the same constants. Yeah, we often use D as an abbreviation for differential, right? So it has no proper differentially algebraic H-field extensions with the same constants. It has certainly differentially algebraic H-field extensions with more constants, because if you just adjoin constants, then that is a differentially algebraic extension. Okay, but it sort of justifies the term H-closed, I think. It's like algebraically closed or real closed. Right. Now, even model completeness is not really the end of the story. It's really, in our book, the main step towards an elimination theory for H-closed fields. And that is what the book culminates in. And but that will involve some extra predicates. For those who are familiar with the model theory, when you want to do quantifier elimination, you often need to add new predicates, but they should be definable in the original structure. So here the two predicates are the following: lambda k and omega k, and here they are defined. They are defined in terms of simply in terms of the differential field that we are dealing with, minus a double dagger, all the minus a double daggers which are strictly dominating one, which are infinitely large, and then all the omega k, consisting of those things where you can solve the differential equation 4y double plus ay is 0 in a non-trivial way. And these are downward closed in the ordering. For example, for KST, the first set consists of all the things that are less than this, basically less than this infinite series that I had earlier on, which actually plays a role, as you see, or it should be less than some initial segment of that series, for some n. So, of course, this definition does not show that it is definable, but this definition here shows that it is definable in a differential field structure. And likewise, omega t happens to be this Okay, so now we can add to our language of ordered value differential fields two symbols, binary relation symbols, and we interpret them in every H-closed fields as follows: A capital lambda b if and only if A is in lambda k times some element b, times this element b, and A omega b if and only if A is in omega k times b. Right, and then the elimination, the quantifier elimination, is saying that every formula in this extended language is equivalent to a quantifier-free formula in the same language and uniformly for all H-closed fields. Right. And here are some, I go a little bit fast at the end because I'm running out of time, I think. And the consequences for definability. There are many of them. If a set is definable, then, one consequence is that T is O minimal at infinity, or locally O minimal, if you like. If you have a set of n tuples, which is definable in T, then if you intersect it with a constant field, if you take its trace on the constants, you get the semi-algebraic set. For those who know about NIP, T has NIP. You can go a lot further. You can introduce a rough dimension theory where any definable set you can assign a dimension, which is one of the numbers from 0 up to n or minus infinity in case it has its empty. And for example, the dimension of S will be n if and only if it has non-empty interior. The dimension will be 0 if and only if it is discrete and non-empty. And you have to be careful here. R is discrete as a subset of T. We equip T with the order topology or the valuation topology. It doesn't matter, they are the same. But in that topology, R is actually discrete. So the dimension of R is 0, according to, you also have a uniform finiteness result if you have a definable set S in T to the power m plus n. There is a bound B, so it's all the finite sections have size at most B. In other words, you can, in logical terms, the quantifier, there are infinitely many, is available for free. Okay, and I promised to end with open problems, so here they are. So we have focused here on the model theory of T as a differential field, but what about exponentiation? The thing is that the exponentiation on T is not definable in T, although it's when you restrict it to the infinitesimals, it is definable. But it's very natural question to ask whether the results that we had can be extended to T viewed as a differential exponential field? Does it have a viable model theory? And Kaplan has some results in this direction. For example, when you expand T with exponentiation and sign, both restricted to -1, 1, then it does have a viable model theory. But there is a lot of work to be done here. It's a difficult problem. Another difficult problem which Alan Garrett has worked on and I hope still is working on, is you can also focus on the logarithmic Transseries, which are in some sense a much smaller field. Namely, a logarithmic Transseries is one where all the transmonomials are just of this form, L0 to the power R0 ln to the power Rn. And yeah, does that have a viable model theory? It would be very good to know, but it seems again a very difficult problem. Right. Okay, I have to stop here. I think I ran out of time already. Thank you.
Thanks very much, Lau.